Okay, hi guys. This is Mr. Noyes again. This is my third video on the dynamic study guides. We're going to go into more detail on some of the things we generally spoke about in the past two videos. So, friction, they kind of go into more depth than the other forces. So, friction, pencils. Okay. So, friction, rub your hands together like that. You can feel the heat coming off because of friction. So, friction always, as we said before, opposes the motion or the velocity that the object has. So, if an object's moving to the right on a surface where there's friction between that object and the surface, there'll be a force opposing that motion. We call that friction. Little f, lowercase f. Okay, so we can skip this page. Now, where does friction come from? If we look at two surfaces in contact, it's like one surface is like, even if it appears smooth, that surface is jaggedy. And then the other surface, even if it appears smooth, could be jaggedy too. Now, these bumps can fit into these valleys, or they can be resting on top of the valley. One bump can be resting on top of a peak, and as you slide these things get, these surfaces, the little peaks and valleys, get stuck into each other, and it takes work to push them out of it. So on a microscopic level, that's what's happening. That's what causes two surfaces to stick, because the uneven surfaces kind of interlock to some extent. Okay, there's two kinds of friction that we're going to talk about: kinetic friction and static friction. If the object is already sliding on the surface, we're talking about it having kinetic friction. And I just call it kinetic friction. I symbolize kinetic friction as Fk. Kinetic means moving. Okay? And so, I don't like this equation. Fk, kinetic friction, is the symbol mu, K, times the normal force of the object on the surface. So, mu K is called the coefficient of kinetic friction. Okay, so every two surfaces has its own coefficient of kinetic friction. So two surfaces might be really slippery, and then it would have a low coefficient of kinetic friction, or two surfaces could be really kind of sticky. That would have a high coefficient of kinetic friction. So every two surfaces has a unique coefficient of friction for when they're rubbing against each other. Okay, so normal force is, if it's a flat surface, normal force is equal to the weight of the object. But if it's a slanted surface, that does not apply, as we'll see. Okay, now also if a slanted force is acting on an object, it will not, the normal force will not be equal to the weight. So if we have an object like this on a slanted force, on a slanted surface, the weight, normal force will be less than the weight. Whereas if we're pushing down, we're going to find this out later. If we're pushing down with the applied force, the weight's going to be something, but the normal force will be bigger than the weight. And if we're pulling up on something, the normal force will be smaller than the weight. Now, by definition, normal force is what the scale would read if that object was resting on a scale. So the scale reading would read more if someone's pushing down on your shoulders as you stand on a scale. The scale reading, the normal force, would be more if someone was pulling down on your shoulders, pushing down on your shoulders. Whereas if someone's pulling up on your shoulders or under your armpits as you're standing on the scale, the normal force, the scale reading would read less than the weight. Okay, so these are kind of important concepts. So if you're on incline, the normal force will always be less than the weight. If someone's pushing down on you at an angle, normal force will be greater than the weight. And if someone's pulling up under your armpits, the normal force will be less than your weight. Okay, so here's some examples where normal force is not equal to weight. If you're in an elevator, the elevator is going up, accelerating upwards. Your weight will be less than the normal force acting on you. The floor pushing up against you, the normal force will be greater than your weight. But if the acceleration is downward, we don't really need to talk about the velocity. Sorry about that. But if the elevator was accelerating downward, here you are in the elevator, the acceleration is downward, the weight will be greater than the normal force acting on you. You'll feel lighter. Okay, so here's normal force. Here's the weight. So if the acceleration is upward, the net force is going to be upward. And so N has to be bigger than the weight. If the acceleration is downward, you're in an elevator, the net force would have to be downward, and so the weight would have to be greater than the normal force. Okay? So, what I'm trying to say is the weight is not always equal to the normal force. Only if the elevator object's going constant speed or is at rest. So if here's the elevator and you're sitting on the floor, the weight will equal the normal force in two cases. If the object is at rest or if it's moving upward or downwards at constant speed. Really what I should say, or if the net force is 0, that means it could be moving. It could be at rest or moving with constant velocity, either up or down. Okay? Okay, so that was very quickly. I'm showing you that normal force is not always equal to the weight unless it's on a flat surface, not accelerating up or down. Okay, I should say the vertical acceleration as well, because you could have horizontal acceleration and normal force would have to equal the weight if it's on a flat surface. Okay, so let's go on. So here's some coefficients of kinetic friction. You can see they're unique for the types of material that are on contact with each other. So let's pick a really small one. So this is a very small coefficient of kinetic friction. Small. That means very slippery, very low friction. Okay, so I hope in our joints they're lubricated with some fluid in a sac for each of our joints and makes very low friction. Now if you have arthritis or you can hear that as you move your joints. Some of that fluid has leaked out as you get older and get arthritis. Okay, let's pick a big one. Here's a big one. Yeah, tires, rubber tires on dry concrete. That's a large coefficient of kinetic friction. So those two surfaces are not friction free. There's a lot of friction. They're sticky. Now you can see that. Okay, whatever. Okay, now kinetic friction force. Now let's talk about the force of kinetic friction. Okay, so this guy is pushing a crate. This crate is going to be this blue dot right here. So there's the applied force. And there's some friction here. I don't know if it's going to be bigger or smaller or the same size as the applied force, but I'll just draw it smaller. Okay, big A means applied force, right? Then we got the weight. And then we got the normal force being the same size as the weight. Okay, so this is my free body diagram. Now notice I did not draw the Earth's, oh, forget that. Okay, determine the net force in X and Y directions. Well, in the Y directions, the A and the W cancel out. I'm sorry, in the Y direction, the N and the weight cancel out. So it equals N minus weight, which equals 0. So there's no acceleration up or down. In the x direction, if F was smaller, then if the friction was smaller than the applied force, then we would say A minus friction. Basically, that would be the net force in the x direction. Now, you could have the friction bigger than the applied force, and that would mean it's slowing down. And so, if friction was greater than the applied force, then F net would equal friction minus the acceleration, and it would be slowing down. That kind of acceleration. The acceleration would be negative acceleration, whereas in this case, you have positive acceleration. This would have negative acceleration if the force of friction was smaller than the applied force. Okay, so let's look at these problems. A brake is sliding to the right and horizontal. What are the directions of the two surface forces, the friction force and the normal force? Okay, so if velocity is that way, let's do this. If velocity is to the right, it's shown by those purple streamer lines right here. Okay, so what are the directions of friction force? Well, friction always opposes the motion. And normal force is always perpendicular to the surface, so the normal force is up and the friction is to the left. So friction is to the left, normal force is up. So that's letter D. Okay. We got, of course, kilograms is mass. Okay, the coefficient of kinetic friction is mu K. Okay, mu is like a backwards Y when you draw it. So get used to drawing it. Okay, the coefficient of friction is 0.25. What is the size of the force of friction? So, F equals mu times N, friction equals mu times N. And so, what are we looking for? Just multiplying 0.25 times N. Now, don't put 4. In this case, N is equal to the weight is equal to mg is equal to 4 times 10. So that's 0.25 times 40. Okay, which is 10. And they use 9.8 instead of what we do for 10. So their answer comes out to 9.8. Okay, don't get confused between friction, the force of friction, and the coefficient of friction. Okay, don't confuse between those two. One thing I should say is that coefficients of friction are unitless. There's no unit, because what they're defined as is F over N. They're defined as friction over N in friction. Well, remember, that's the equation, but coefficient is friction over N, and the units would cancel out. That'd be newtons over newtons. So there's no units for coefficient of friction. But for friction, the units are force units, newtons. Okay, static friction. Static friction is the friction you have when you push on something or pull on something and it doesn't budge, because those little hills are interlocked, and it's going to take more force to push those little bumps out of the little depressions, like I tried to explain before. So as I apply a force on this blue block, it doesn't. I keep on increasing the force, and it doesn't even move. And at some point, it will budge. Okay? So that's called the friction right here. That's equal to the applied force. But when it's not moving, that's static friction over there. And the force that's causing it not to move is the actual static friction. Static means at rest. Now, the coefficient of static friction is the maximum coefficient of static. I'm sorry, let me say it again. The maximum static friction is equal to the coefficient of static friction times the normal force. Okay, it looks just like the other equation, except I got S instead of K. Okay, but the weird thing about this is you can push on something that's like resting on a table, and you gradually increase your push until it just starts to budge. And that's what we're concerned with. What's the maximum friction that resists the motion of an object? So basically, if you push on something and you keep on pushing, okay, you push on something a little bit, it doesn't move. You push on it more, it doesn't move. You keep on increasing that speed until it budges, and then that will be my when it starts to move, the moment it starts to move, that applied force will be the maximum static friction. And that's how you compare it to the static coefficient of friction. So, in all these cases, the applied force equals the friction, but the maximum applied force, where it starts to budge, is equal to the maximum friction, static friction, which is used to calculate the static coefficient of friction. Sounds like a lot of words. Okay, so here, this graph is kind of an important graph. If here's an object, and I keep on increasing the applied force right here. That's on the x-axis. I keep on increasing it. And this red line right here, then, it doesn't move. The force, as I increase the applied force, the frictional force increases to a maximum point where it peaks off. Right there is my maximum friction. You can read that off the y-axis. So, and then after it starts moving, kinetic friction kicks in. So, once the thing starts moving, you can see that the applied force, or the kinetic friction, will be less than the maximum static friction. Okay, so this is a classic graph. If we have a lab, you can, on this, I hope we do, you can see for yourself that this graph is what forms. Okay, so key points. The maximum applied force that can be applied without it moving would be where the peak is right here. Where the peak is right there. And then you just read it off the y-axis. It looks like 40 newtons here. And then after that, it drops to some value right here. Then you just read across. And that would be right there. That would be your kinetic friction right there, on the 30. Okay, so there's no motion, as you can see right here. There's no motion as when it's at rest and you're trying to push it into motion, and that static friction will increase to a maximum. And once it's sliding, I don't care whether it's moving constant speed or accelerating, the kinetic friction will be a constant. Okay, so we can continue. Oops, what's going on? We can continue to this table, and same table. We already showed you this right here, coefficient of static friction. Oops, no, I already showed you the kinetic coefficients of friction. Now you can see the static friction is always bigger than the kinetic coefficient of friction. The coefficient of static friction for two of the same surfaces is always bigger than the coefficient of kinetic friction. You can see that pattern. Now when it's really slippery, it doesn't matter. But that's when it's really slippery, it really doesn't matter. There is no difference, because those little bumps are so filled in with fluid that there's no resistance. Okay, so let's do the problem. 4 kilogram box. Okay, again, that's mass. Kilograms is mass. Static friction, the coefficient of static friction, so that's mu s. What is the largest force again? Okay, so I'm looking for what's the biggest applied force before it starts to slide. So there's my applied force, and here's my static friction maximum. So basically, F S max is equal to coefficient of friction, static, times normal force. But the normal force on a flat surface is equal to weight, is equal to mg, is equal to 4 times 10, is equal to 40. Okay, coefficient of static friction is 0.45. So basically, 0.45 times 40. Let's see. 0.5 times 40 is about 20. So the one closest to 20 should be that one. Now they get here. Hold on. Double check that on my calculator. Sorry. Okay, I get exactly 18. So I guess they used 10 instead of 9.8 this time. Okay, we talked about tension. We can skip this. This is pretty straightforward. The tension is like the normal force. Okay, here's one. Might as well do them. Okay, if a lamp is hanging from a rope, tension is supporting it. It's in the cord by the rope, and the weight. I know the tension is equal to the weight, so that I like to put it tension in a box because big T means something else later on in physics. What is the tension force being supplied? Okay, so equals mg. This is right before the hurricane, so I'm getting those messages. Okay, so the mass is 25 times 10 is 250 newtons. The mass is 25. The acceleration due to gravity is 10. So I guess they're using 10 now instead of 9.8. Okay, how about this one? A crane lifts. So I'm lifting this up. The acceleration is upward. 3.0. Now, if the acceleration is upward, I know the F net is upward because they always are in the same direction. So the tension is going to be bigger than the weight. Okay, F net is equal to MA, yes, but it's a bigger force minus a smaller force. Okay, so the tension, that's what I'm looking for. The weight is mg, so it's 400 times 10 in net force is ma, so the mass is 400 times positive 3. I don't use plus or minus because I'm using my diagram. Okay, is tension minus 4,000. So let's see, that's 1,200. No, yep, equals T minus 4,000. So T is equal to 1,200 plus 4,000. So that equals okay, so that equals 6,200 newtons. Whoa, what's going on? Sorry, miscalculation. I get 5,200. Okay, so they use 9.8, so that's why they get 5120. Okay, so now okay, these are diagonal force problems, and inclined planes are a special case in which we should know. Okay, so let's see this. So this guy's skiing down the hill, and let's be able to draw a free body diagram of that. So let's say he's accelerating downwards. So the acceleration is downwards. So you know what? I'm gonna just do it underneath this from scratch. So here's the object. There's the weight. The weight's going to be broken up into X and Y components. Okay. So now the normal force is perpendicular to that surface. Normal force is perpendicular to that inclined plane surface. you're going to have friction, a little bit of friction, even if he's skiing down. Okay, those are the only forces we have. Now, actually, there's the x component of the weight. The x component of the weight, I'm going to call that Wx, is what's bringing it down the incline. And this y component right here of the weight is what's keeping it stuck into pressed into the incline. So let me erase this. So whenever you're in an incline, it's the x component of the weight that's making you go down the incline. Okay, now this angle right here, the slope angle, is the same as this internal angle right here. Okay, they're congruent. This angle right here, this triangle right here is congruent to this triangle. And that's why. So those two angles are the same. So Wy is equal to W times, because that's the y component, W sine of theta. Then Wx is W cosine of theta. Weight is equal to mg. And coefficient of friction, depending if it's moving, let's say it's moving, is the coefficient, the kinetic friction is the coefficient of kinetic friction times the normal force. And in this case, the normal force on an incline, normal force is always equal to Wy, the y component of the weight. Okay, so when you're doing inclined plane problems, it's important that you can set this up like that. Now, there's really three forces acting on the box, not 1, 2, 3, 4, 5. But when I draw the x and y components, I'm just breaking it up, and the two red arrows are really what the blue arrow the weight arrow is. So I'm kind of getting rid of the weight, the blue arrow right there, when I break it into its x and y components. Okay, so if he was going down the skier was skiing down the slope, I would say the net force would equal Wx minus the friction. Then I could say W cosine of theta minus mu n, mu mg. No. N would have to equal not mg, the weight, but Wy. Okay, which would be W, the weight, times sine of theta, or mg sine of theta. Okay, so that's if he's accelerating down and speeding up. If he was accelerating down at a constant, if he was sliding down at a constant speed, with increasing velocity. If he was going with constant velocity, with constant velocity, then F net would be 0, acceleration would be 0, F net would be 0, and we could say that Wx is equal to the friction, because those two forces would have to be equal and cancel out each other. Okay, so those are fancy problems. We'll deal with those later. Okay, elevator problems. I just kind of did. These are important. Let's just do one at a time. Okay, let's just, I'll work this problem out underneath it, then we'll solve it. You can look ahead and see how step by step I solved it. So let's look at this problem right here. Okay, this is mass. Okay, we're kind of leaving friction right now, and we're going into elevator problems, which are really important. Calculate the tension force in it. Okay, so we're looking at, instead of normal force and weight, we're looking at tension and weight, no friction. Okay, so it's moving at a constant speed. This is that part A. Okay, A would be 0 if you're moving at constant speed. That means net force would be 0. That means T and W cancel each other out. So tension would equal the weight, which is equal to mg, which is equal to 1800 times 10, which is equal to 18,000 newtons. Okay, that's part A. How about part B? Moves at constant speed downward. Now, I don't care if it moves downward or upward at constant speed. The point is, it's moving constant speed. If you're going constant speed, what's your acceleration? It doesn't exist. So what's your net force according to second law of motion? 0, ma. A is 0. So there's no difference. This applies, and I could just say, oh, okay, tension. Same thing applies, 18,000 newtons. Okay, what if you're accelerating upward at a rate? We're accelerating upward rate of 2.4. Okay, so part C. Here's the thing. Acceleration is upward, 2.4 meters per second squared. So what's net force? ma. So the mass is, again, 1800 times 2.4. The acceleration. So we get 4320 newtons. Okay? For the net force. I want the tension. So the acceleration is up, so the net force has to be up as well. Okay? Direction of the acceleration and net force are always in the same direction, because one causes the other. Net force causes the acceleration. So here's my tension, here's my weight. My tension has to be bigger than the weight. My tension has to be bigger than the weight if it's going to be accelerating upward. So net force equals the bigger one, tension minus the weight. So the tension minus the weight. Okay, I already had the weight as 18,000 from before, mg. And then this would be 4320. So the tension is equal to 4320 plus 18,000. So that'd be that would come out to be 22, 3, 22,320 newtons. Okay. Upwards. Of course, all the tensions are upwards in this case. Then what if it was accelerating downwards with the same acceleration? Well, so letter D. If it's going downwards, acceleration is downwards, F net is downwards. And I already did all the math. F net would be 4320. That would mean the weight is bigger than the tension. I want to say normal force because it looks the same. So, F net is equal to weight minus tension. I already had the values up here, right? 18,000 minus T is equal to the net force, 4320. And so, negative T, let's get the 18,000 on the other side, is equal to 4320 minus 18,000. Right? So, 4320 minus, I get negative 13,680, which makes T equal to 13,680 newtons. Okay, these are very important for these kind of problems. Elevator problems are very important for the next unit when we talk about centripetal force of vertical circles. Okay, so I just did all that. You can go through this step by step if you want. Okay? And I mean, they're showing you how to do it as well. But I just wanted to show you all the steps. Okay, so let's go back to the inclined plane problems. Okay? Which I introduced and then just left. Okay, so here, draw a free body. Okay, so here's the weight. I always make normal force shorter. Here's kinetic friction opposing the motion. Velocity is that way. Okay, and then we have that. Those are three forces acting on it. Okay, let's break this up. Let's break W up into WX, three-finger rule, and WY. There's WX, here's WY. And the inside angle is the same as the ramp angle. So the ramp ramp angle is 28 degrees, and inside angle between W and WY is 28 degrees. So there's my FBD. Now just the black arrows would be a good FBD. You don't have to include red components, but when you saw a problem, you sure do. Calculate the normal force on the box. Well, normal force, I don't care if it's accelerating or not, is equal to what? The y component. The y component, use your equations on your equation sheet. Remember, qy is equal to q, which in this case is w, times sine of theta. So that equals mg, which is what weight is, times sine of 28. I get 14.08 newtons. 14.08 newtons. Okay, calculate the friction acting on the box. Okay, well, F equals mu times N. They gave me the coefficient of friction up here. So the force of friction is not the coefficient of friction. It's 0.3 times the normal force. We just saw 14.08 up here. So times 0.3 is 4.23 newtons. Let's calculate the acceleration of the box. Well, to find the acceleration, I need to have the net force. That equals ma. So to find the net force is, since it's accelerating down the ramp, Wx has to be bigger than Fk. Wx has to be bigger than Fk. So this would be Wx minus the kinetic friction is equal to the mass 3 times the acceleration. Okay, Wx I don't have yet. Wx, use that Q equation. Wx is Q times cosine theta. In this case, Q times cosine of theta, mg cosine of theta, minus Fk, I just did up there, 4.23. Equals 3 times A. I'm trying to solve for A. So mg is 3 times 10 times cosine. What's the ramp angle? 28 minus 4.23 divided all by 3 is equal to A. So I get A equals 7.4 meters per second squared. That's the acceleration of the box down the ramp. Okay. Okay, notice that. Notice that this N is not equal to the weight. N is not equal to the weight. It equals the WYP. So that's a trap that people fall into. Those problems are difficult. You got to get used to those.